Life. Do you know what life is? It is cosmic dust, a random temporary phenomenon, a zero without a stick, a speck on a bare spot, of no significance on the vast stage of the universe. How many times have you heard such derogatory statements about what we call life? The most mysterious phenomena in the universe, black holes, magnetars, dark matter, are not the most mysterious. We see evidence of their existence everywhere. Against the backdrop of the entire cosmos, life seems like an anomaly. Only the manifestation of life is not found anywhere outside our planet. Life. What is it? Amidst hundreds of trillions of kilometers of empty rock and gas, something so strange that it's able to oppose itself against everything else. We are living people, flesh and flesh of the universe we see, and we are quite clearly part of it. At the same time, the universe doesn't seem alive to us. Have you ever wondered what the fundamental difference is? What's the difference between living and non-living matter? And where is the line where one ends and the other begins? If you look at it through the eyes of ancient man, there are differences. Inanimate matter, for example, a huge rock in the dark may well resemble a live bear. But only living matter, a live bear can chase you in the forest, and no matter how much you dash through the trees, catch you and tear you to pieces. Inanimate objects never do anything so purposeful. A huge boulder rolling down a mountain isn't really chasing you. That's how ancient people thought, no wonder, because they'd never seen a homing missile. It was also anciently believed that there must be something, some animating factor that makes one matter behave very differently from another. Aristotle, for example, believed that the peculiarity of living things is their ability to initiate movement without external influence. He believed that when the same boulder rolled down the mountain, it would never move again, unless something or someone had an effect on it. But living matter, such as a sleeping bear, can be at rest, and then without any influence, take it and start moving. But Aristotle was wrong. Modern science easily reveals the weakness of such generalizations. You could say that a bear also starts to move solely because of external influences. For example, a change in temperature changes the chemistry of his body and he wakes up. And on the other hand, a uranium nucleus, which we certainly don't consider to be alive, can remain unchanged for billions of years and then suddenly and abruptly, without any outside influence, and then suddenly and abruptly disintegrates. Aristotle was absolutely right about something. He was right to call life a fundamental phenomenon of nature. You say, well, everyone in Aristotle's time thought that. Almost everyone thought that the universe was mainly made up of what we now call the biosphere, of the Earth. If the biosphere of the Earth is the main thing that you see and know about in your lifetime, throughout your life, you would naturally think that trees and animals are at least as important as rocks and stars. Yes, indeed, only after hundreds and hundreds and hundreds of years. Discoveries in astrophysics have shown that the universe is not only is it vast and completely indifferent to the Earth, but that it's described by universal laws, which don't mention life at all. Charles Darwin explained the origin of life in a language that did not require any specific knowledge, and even today, having studied many of life's subtle mechanisms, we still haven't found any special physics in them. After all this, to call life a fundamental phenomenon of nature and beyond would be ridiculous. The very concept of nature in the broadest sense has become identical with the concept of physics. From the point of view of the modern average person, the differences between living and non-living matter too will almost always be obvious. At the macro level, we distinguish animate from inanimate, by eye. But if we take any living being and disassemble it into atoms, we will see that they are one in the same atoms of which stars and planets are composed. The same atoms make up what is living and what is not. What makes inanimate matter alive? No one has ever been able to find the very magic property that distinguishes living things from inanimate objects. For a long time after Aristotle, we kept on and on and on missing the essential true understanding of what living matter is. And now modern biology no longer waits to discover something that endows matter with life. For we have finally been able to find the very basis of life, the first step, if you like, where it all begins. Imagine a pile of stones being tossed methodically into the air. After each throw, there is a non-zero probability that the stones will lie on top of each other, forming a certain construction. And this construction will have a set of properties that a mere pile of stones by itself does not possess. So it will be more than just a sum of parts. This phenomenon is called emergence. Emergent is the emergence of properties of a system that are not inherent in its elements separately. There are many examples of such synergy in nature. Of course, the manifestation of some emergent properties is less likely, some more so. You'll see what I mean in a moment. By combining certain atoms in a certain sequence, we get a structure with properties that a simple bunch of the same atoms don't have. The name of this structure is a molecule. Now we realize that the basis of life is not at the level of individual atoms, it is higher. The basis of life is molecular, and the distinctive property of living molecules is that they provoke the environment they are in to copy themselves. Yes, some configurations of atoms do tend to replicate, that is, to make copies of themselves with the help of the environment. These configurations of atoms we call genes. A gene is an emergent property of atoms. As emergent a property as the complex fractal patterns of a snowflake, or the ripples on a sand dune, or the giant geometrically regular hexagon Onan Saturn. The emergence of these emergent properties is, of course, much more likely than the origin of life. Nevertheless, all of the above are nothing but systemic effects. That is, the atoms themselves are not alive, but when they are combined in a certain sequence, their emergent property is immediately manifested. A synergistic effect in which this configuration of atoms will begin to organize the environment in a certain way, creating similar configurations of atoms. There are a lot of examples of emergent properties in nature, and I could not list even a small part of them if I wanted to. For this reason, it is not surprising that no special physics has been found in living matter. For the emergent property of physics is chemistry, and the emergent property of chemistry is biology. Piece by piece, coming together, atoms combine to form molecules, which in turn form whole organisms. The very magic that has been tried to be found in living organisms is nothing but the manifestation of emergent properties in matter. When micro-level elementary processes combine to create incredibly complex macro-level phenomena. For the same reason, people who look for the center of consciousness in the brain have a very poor understanding of what they are doing. So, once upon a time on planet Earth, no one knows exactly how or where, matter exhibited an extremely rare and very, very unlikely emergent property. Under uniquely favorable conditions, the first replicator spontaneously emerged from a bunch of atoms. Having appeared, it started to multiply, and that's it. Having uncontrolled reproduction with limited resources, we get competition. Self-copying of replicators is not perfect, due to which mutations arise, mutations and generate variations of genes, which in turn generate variations of species. Competition plus species variation equals natural selection plus time equals evolution. Yes, all life on the planet is based on replicator molecules we call genes. So there is no division in the universe between living and non-living matter. Matter is the same, and life is simply an emergent property of it. Simple? But does that somehow answer the question of what life is? A gene is the smallest indivisible element of hereditary material that can be passed from parent to offspring. Genes determine the whole organism, what it will be like, what its functions, traits, and properties will be. Genes are the instructions by which the whole organism is built. Modern science tells us that what the organism will be is determined by genes only half. The other half is determined by the environment. This formulation really pisses me off because as it stands, it gives a poor understanding and belittles the true importance of genes. Roughly speaking, it's like if tomato seeds could sprout red cacti by planting them in the desert. From my perspective, a good formulation would go something like this. Genes imply some variation in the characteristics of an organism depending on environmental conditions. So, a gene is only capable of being a replicator in a certain habitat or niche. A niche is the environment in which an organism can survive and produce offspring. And characteristically, from this point of view, the organism itself is a niche for genes. Now you probably don't get the joke yet, but soon you will. Richard Dawkins, who for some reason everyone knows only as the planet's foremost atheist. In fact, he has much more impressive merits and initially became popular not for this reason. In 1976, Dawkins published a book, The Selfish Gene, in which he greatly deepened the theory of evolution. Unlike Darwin, who believed that the fittest version of a species survives, Dawkins proves that in fact the most adapted variant of a gene survives. Thus, all evolution ensures the well-being of the genes that copy best. Yes, the unit of evolution is the gene, not the organism as many believe. For example, the genes for a huge peacock tail clearly do not make life easier for the individual peacock or the peacock species as a whole. But it is these genes that have proven to be the most successful compared to their direct competitors. Hence the name, the selfish gene. The main feature of the replicator is that it is always the cause of its copying. That is, it forces the environment to copy it. Thus, biology is primarily, come to think of it, the science of studying the effects of genes on other matter. What is a bear? It's a huge receptacle of genes. Take, for example, the insulin gene. It can't replicate itself. It critically needs the presence of all the other genes in the bear's body. But that's not all. It also needs genes from other organisms in the external environment. The bear cannot survive without food, and the genes to produce that food are only present in other organisms. So the genes work together to design the bear's body, making it do lots of different things, including hunting, so that they, the genes, can copy themselves. The bear's body is the immediate environment that the genes manipulate for their own replication. You see? They create the bear and program its behavior, forcing the animal to follow algorithms designed to copy itself. No, not the bear, but the genes that are in its body, and to do so at all costs. Note again, the bear itself is not a replicator. The bear does not copy during reproduction, and even less does it induce its own copying. A new bear is created anew from the blueprints embedded in the DNA of the parent organisms. The organism itself is not a replicator. It is part of the environment, the replicators. Usually the most important part after all the other genes. The rest of the environment is the type of habitat an organism can occupy, such as the top of a mountain or the bottom of the ocean, and specifically the way of life in it, such as a hunter or a filter feeder, which allows the organism to live there long enough for replication of its genes to occur. So the organism is the nearest environment that replicates the actual replicators, that is, the genes of that organism. Previously, for example, a bear's nose and its den would have been classified as a living and non-living object, respectively. But there is no fundamental distinction at the heart of this division. The role of a bear's nose is not fundamentally different from that of its den. Neither is a replicator, although new examples of both are constantly being created. Both the nose and the den are just parts of the environment that the bear's genes manipulate during their replication. The genes that need to cooperate in order to replicate join together in long chains, DNA chains. From these chains, different organisms, such as microbes, plants, or animals, are built. These organisms are what we think of as living organisms, but it follows from what I have said that living, in relation to parts of the organism other than DNA, is, well, at best a title of courtesy, nothing more. This understanding of life, which sees organisms as part of the environment in relation to genes, has been at the heart of biology since Darwin's time. But it was largely ignored until the appearance of Richard Dawkins's work, The Selfish Gene, in 1976 and the extended Phenotype in 1982. Living molecules genes are simply molecules that obey the same laws of physics and chemistry as non-living molecules. They contain no special substance and have no special physical properties. They just happen to be replicators in certain environments. Or rather, not even that. A gene can be a replicator most of the time only in a very limited number of environments, while in a huge number of other environments it will not be a replicator. So why have I suddenly decided that life is a fundamental phenomenon of nature? Why is it worthy of this status? What is so special about life in the vastness of the vast universe? Because the influences seem negligible. We don't know if there's life beyond the Earth until we've met it. But even if it is widespread, its manifestations are apparently too negligible to register. Looking up into the sky, we see an active universe brimming with diverse, powerful, but completely inanimate processes. Galaxies spinning, stars condensing, igniting, burning, exploding, and collapsing. High-energy particles, electromagnetic and gravitational waves propagate in all directions. And it doesn't seem to matter very much whether there is life among all these tectonic processes, for it is unlikely to be able to affect any of them. If a huge solar flare were to engulf the Earth, which in itself is an insignificant event from an astrophysical point of view, our biosphere would instantly become sterile, but the sun would be as affected by this catastrophe as a raindrop would be by an erupting volcano. Our biosphere, given its mass and energy, is a tiny, tiny fraction of even the Earth. That said, when it comes to mass, the solar system is called the solar system for a reason. In astronomy, it is considered a well-worn truth that the solar system consists mainly of the sun, whose mass is 740 times the mass of all the local planets combined. Yes, the solar system is mostly the sun, and maybe Jupiter to some extent. With that math, everything else in the solar system except the sun and Jupiter can be called mere impurities. In fact, the entire solar system is a negligible component of the Milky Way, of a galaxy that is itself unremarkable among many others in the known universe. Stephen Hawking once said, "The human race is just chemical dirt on a medium-sized planet, orbiting the most ordinary star on the outskirts of one of the hundreds of billions of galaxies." And I probably don't know anyone who would argue with that, except it's not true. Do you hear me? This view is the deepest misconception of modern times. Ask yourself the question, the basis of life is the gene. What is it? A gene is a piece of hereditary information, a bear, a human, a flower, a bacterium. Everything we conventionally call life is just the way genes copy themselves. The more accurate information a gene has about its environment, the more successful it is at reproducing. Because it has accurate information about its environment, it can live in that environment and reproduce in that environment. Genes with more accurate information about the world displace genes with less accurate information. The vast majority of genes with incorrect or inaccurate information about the environment could not survive in it long enough and/or replicate. Survival of the fittest to the environment, right? What is environmental adaptation? Adaptation to the environment is the presence of reliable knowledge, that is, objective information about that very environment. Not that genes can know anything. But evolution is about weeding out those genes that have less complete and less reliable information. The human eye is not perfect. We can't even begin to comprehend how far it is from seeing the universe as it is. But it was good enough to allow humans to perceive things more or less accurately. And, of course, through a combination of factors, become the most efficient species on the planet. And all because the genes responsible for the formation of the human eye store in themselves enough accurate information about the surrounding world so that the whole organism could adequately perceive this world. And this applies to all living things. Genes carry out very precise interactive control of reactions of a complex environment, of an organism to everything that can happen to it. And this control is aimed at causing a very specific response of the environment to genes, namely to replicate them. And the more situations outside, the more genes are able to digest without dying, the more successful they are. In this context, the human brain is potentially the best thing that genes have been able to build. Well, from what we know, the more the information in the genes matches the conditions of the environment, the more copies of those genes will be left behind. So you could say that evolution is essentially a kind of computational process, and genes are literally embodied information about the environment. Realize this: all the sensory experiences that you get from living your life, the colors and geometry you see, the sounds you hear, the hardness or softness of the ground under your feet you feel, your ability to move through space, your ability to feel that water is wet and mud is viscous, to feel the play of the wind on your skin. After all, you have manipulators in the form of hands, all of these things. But they didn't come from the ceiling. They came from something that over millions of years of evolution have bred genes that carry the most reliable knowledge of the environment. And this knowledge is embodied in you. It is because of this embodied knowledge of the world that you are able to interact with the environment, to receive stimuli, to respond to stimuli, to respond to stimuli. And vice versa, you are also capable of giving stimuli to the environment and receiving a response from it. Humans don't have the genes to see the entire spectrum of electromagnetic waves, or all the dimensions predicted by M-theory. Because we don't have any genes, it's possible that some things in the universe are fundamentally unknowable to us, and maybe that's a good thing. But we have genes that give us a predisposition to unprecedented abstract thinking, through which we can learn about some phenomena that are inaccessible to us at the level of the senses. That is, genes carry knowledge of their niches. Everything that is of fundamental importance with respect to the phenomenon of life is determined by this property, not by replication per se. Having reliable knowledge is primary, because genes with unreliable knowledge are not viable and die out quickly. Genes that replicate the environment less accurately are always inferior to genes that replicate it more accurately. In this case, we are talking about better adaptation of genes to their niche. Why is it the presence of accurate knowledge and not reproduction that is primary? Because we can imagine a species whose genes are not capable of replication, but are adapted to preserve their form from external influences. For example, able to resist corrosion and other destruction. It's unlikely that such a species could occur naturally, but it could be created artificially. Once the production of these artificial organisms stops, the number of examples of each non-replicant gene cannot increase. But it will not decrease either, as long as the knowledge that these genes contain is sufficient to implement the survival strategies of these genes to the niche they occupy. And here we can see that the survival of valid knowledge, and not necessarily of a gene or any other physical object, is fundamental. Therefore, strictly speaking, some part of knowledge, not a physical object, is adapted to the niche. If the adaptation is successful, then that knowledge has the property that once embodied in that niche, the knowledge will tend to remain there. A gene in the form of its physical shell is not so important because in the case of a replicator, the physical material that realizes it is constantly changing. A new copy is assembled from non-replicant constituents at each replication. On the other hand, non-replicant knowledge can also be successfully embodied in various physical forms, as in the case of transferring an old record from a vinyl record to a magnetic tape and then to a CD and so on. After all, perhaps humans will one day copy the knowledge contained in their genes onto the most reliable future medium available to them, replacing their fragile biological component with something more robust. And it would be strange to call these people of the future inanimate, because if you, for example, do not believe that the body is a special vessel for the soul, but at the same time you claim that artificial intelligence is impossible, then it's the same thing. It's literally the same as if you were saying that the brain is not a physical object. But the terminology is not that important here. The point is that although all known life is based on replicators, it is actually built around one single phenomenon: knowledge. In that case, what then is life? Life is physically embodied knowledge of a niche that forces its niche to maintain the existence of that knowledge. And I am well aware of what a set of words and the ravings of a madman this may seem, if you have not delved properly into what I was talking about. But this is perhaps the most profound definition of life that we can give summarizing all of the above. However, any skeptic will stop me and say that knowledge is an anthropocentric human concept. That is, knowledge is a thing that is important to us humans because our ecological niche depends on the creation and application of knowledge. Outside of humans, the concept is meaningless and unimportant to the rest of the universe. But a skeptic would be critically wrong. Knowledge is not only important for Homo sapiens and not only on planet Earth. Let's look at the astrophysical implications of knowledge. Today we have a cool theory of stellar evolution describing the structure and development of stars. But 100 years ago, we didn't even know the source of solar energy. The best physics of the time gave only the false conclusion that whatever the source of its energy, the sun could not have shone for more than 100 million years. Then nuclear physics was discovered and with all its subtleties applied to the physics of the stellar interior. Now we understand why stars shine. For most stars, we can tell what their temperature, color, luminosity, and diameter were at each stage of existence. We can find out the duration of each of these stages, tell what elements the star creates by nuclear transformation, and so on and so forth. This theory has been repeatedly tested and supported by observations of the sun and thousands of other stars. We can use this theory to predict the future development of the sun. It says that the sun will continue to shine with great stability for about 5 billion more years. Then, it will enlarge by a factor of 100 and become a red giant. Then, the sun's outer shell will dissipate into the surrounding space, forming what's called a planetary nebula. The bare core will become a gradually cooling white dwarf. I think you know all this. In tens of billions of years, the white dwarf will cool down enough to give off no visible radiation, becoming a black dwarf. But will all this really happen with the sun? Is it possible that every star of the same mass and composition that formed 5 billion years before the sun has already become a red giant, as the theory predicts? And is it possible that some seemingly inconsequential chemical process on the tiny planets orbiting these stars could alter the course of such cyclopean processes? Is it possible that a bunch of chemical dirt could affect unimaginable nuclear and gravitational processes that operate with immeasurably more mass and energy? If the sun does become a red giant, it will engulf and destroy the Earth. And if our descendants are still on Earth by then, they probably won't want that to happen. They'll do everything in their power to prevent it. Are we 100% sure there's nothing they can do? Of course, our current technology is too weak to handle such a task, but that doesn't mean that this task will remain insurmountable in the future. In fact, we already know roughly in general terms what it would take, namely the removal of matter from the sun. And we have another 5 billion years to perfect our crude plans and put them into practice. Now pay attention. If our descendants save themselves in this way, it means that our current cool theory of stellar evolution as applied to one particular star, the sun, is completely wrong. And the reason for that is that it doesn't take into account one of the fundamental parameters. It takes into account the fundamental physical effects associated with nuclear and electromagnetic gravitational forces and hydrostatic and radiation pressure. But not life. It doesn't account for the effects of life on stellar evolution. You see, it is impossible to predict the future sun without taking into account the future of life on Earth, and in particular, the future of knowledge. The color of the sun in 10 billion years will depend on the gravity of radiation pressure, on convection and nucleosynthesis. It does not depend at all on the geology of Venus, chemistry, Jupiter, or the pattern of craters on the moon, but it does depend on what happens to life on planet Earth. It depends on politics, economics, and the outcome of wars. It depends on what people do, what decisions they make, what problems they pose, what values they cultivate, and how they behave toward their children. Such a theory does not follow from a law of physics or any other fundamental principle known to us. It can only be proven in high-level human language. Thus, theories about the activity of life are necessary for astrophysical predictions. Even if you are the most penultimate skeptic and pessimist and do not believe that life on Earth will last this long, you still cannot escape the same conclusion. For even if the human race's attempts to survive are ultimately futile, the cosmos is vast. And if some intelligent life in some galaxy ever manages to survive for billions of years, it means that life is inevitably important in the general course of the physical development of the universe. Thus, throughout our galaxy and any other galaxy, stellar evolution depends on whether and when and where intelligent life evolved. Yes, we have not yet received any credible evidence of extraterrestrial life, much less extraterrestrial intelligent life. At this point in the universe as we see it, life has not affected anything of any astrophysical significance. But as you know, the speed of light is severely limited in the universe, and as we look up into the sky, we see the past, and we can only see in less detail the past that's spatially close to us. The further into the universe we look, the more distant the past we look, and the less detail we see. And that's where things can happen, you know. When our theory of the structure of the Milky Way becomes more advanced, we will be able to make more accurate predictions, but again only on the basis of assumptions about the distribution and behavior and intelligent life in the galaxy. If these assumptions are not accurate, error in predicting the distribution of spectral classes will be almost as inevitable and gross as if we were mistaken about the composition of interstellar gas or the mass of a hydrogen atom. Cosmologists John Barrow and Frank Tipler looked at the astrophysical manifestations that life would have if it survived long enough. They found that life would eventually make a huge qualitative change to the structure of the galaxy, and subsequently the entire universe, and that eventually it would be quite capable of dominating everything that happens, just as it now dominates the biosphere of the Earth. Any theory of the structure of the universe in all but the earliest stages must center on what life will or will not be doing by then. This cannot be avoided, nor can we dismiss the fact that the future of the universe depends on the future history of knowledge. We are used to justifying the small importance of life by giving too much weight to general quantities, such as the size of mass and energy. From the point of view of modern science, these are indeed good measures of significance, but in the context of life processes, they have little applicability. Therefore, there is no reason why this should remain the case in physics. The biosphere itself already presents many counterexamples. For example, in the 3rd century BC, the mass of the human race was only about 10 million tons. One could conclude that there is little possibility that the presence of such a small biological mass could have been the cause of any physical processes that set in motion many times larger masses. However, it was at that time that the Great Wall of China was built, the mass of which is 300 million tons, that is 30 times larger. Moving billions of kilograms of stone is one of those things that people do all the time. Today, it only takes a few dozen people to dig a railroad tunnel by removing millions of tons of earth. These thoughts are even stronger if we more fairly compare the mass of the stone moved with the mass of that tiny part of the brain and the of an engineer or an emperor, which embodies the ideas that made the job happen. 100 years ago, we stoked our stoves with wood. Now the human race may have enough knowledge to destroy entire planets if its survival depended on it. Even unintelligent life has greatly transformed the substance of the Earth's surface and atmosphere, which is many times its own mass. All the oxygen in our atmosphere, about 1,000 trillion tons, was created by plants, and thus was a side effect of gene replication. That is, the molecules of the offspring of one single molecule. Life has an effect not because it is characterized by greater dimensions of mass or energy than other physical processes, but because it has greater knowledge. By the macroscopic effect that knowledge has on the outcomes of physical processes, it is at least as important as any other fundamental physical characteristic. But there's more. In the previous video, we concluded that we probably all live in an amazing place, the multiverse. Let's compare it to the live bear, the constellation of the Great Bear. Live bears in many nearby universes are anatomically very similar. Not only their genes, but their entire body has this property. However, there is no such regularity in the constellation of the Great Bear from one universe to the next. The shape of the constellation is highly susceptible to such a phenomenon as chaos and would depend entirely on the initial state of the galactic gas from which the stars were formed. This state was random at the microscopic level, very random in different universes, and the process of star formation from this gas included all sorts of instabilities, increasing the scale of variations. As a result, the arrangement of stars that we observe in a given constellation exists only in a very limited range of universes. Most close variants of our universe also have constellations in the sky, but they look different and even quite different. In an individual universe, the most striking structures are galaxies and galaxy clusters, aren't they? But these objects have no discernible structure at all in the multiverse. Where there's a galaxy in one universe, in the multiverse there are rows of galaxies with very variable geography that are close to each other in the universe only in certain general ways, as the laws of physics apply to all of them. Yes, most stars have a fairly precise spherical shape throughout the universe, and most galaxies have a spiral or elliptical shape. But nothing extends far into other universes without changing the details of its structure beyond recognition, except in the few places where there is embodied knowledge. In such places, objects stretch across a vast number of universes while remaining recognizable. The genes with the best adaptation will have the same structure across a vast range of universes. If only you could observe the entire multiverse through a telescope, life and its consequences would be obvious at a glance. Places in the universe touched by life would be different from other places, just as cultivated fields are different from wild jungles in satellite images. Just as crystals are different from the solution in which they grew, except in the few places where there is embodied knowledge. And despite the seeming insignificance of life, it is life that gives rise to the largest scale regular discernible structures in the multiverse.